Good morning. Good morning, physics students. I'm going to do a little video here to help you get through this next worksheet. Just due to the fact that we didn't get to cover a lot of acceleration stuff before I left, and I don't know what you guys covered before. So we're going to do worksheet 4, which is the next two pages, 24 and 25. You're going to go ahead and graph this data, position versus time, draw your best fit curve through there, and answer the following questions. And you're going to have a curve just like the wheel and axle should have, or if you go all the way back to your first page in the packet, which is this one right here, you have this curve. And then keep in mind that your average velocity is when you draw the straight line from 0 to 6 seconds. It could be from 2 to 4 seconds. And then our instantaneous is when you draw a tangent line that touches any one of these points, which I believe on this worksheet, where the following one, we drew a tangent line at every single one of these, and it gave us the instantaneous velocity at every second. Okay, so keep those in mind. And in this case, 0 to 6, I think the slope was 30 centimeters per second. And then from 2 to 4 was 30. And then the mid-interval time, if you take 0 and 6 seconds, 3 is half of that, right dead smack in the middle, and now it's 30. So those are always going to be equal, and you can tell by the slopes that I drew here. So they're going to be equal. So the average velocity from 0 to 6 is the same at 3 seconds as your instantaneous velocity. So let's go back to here. So the front page should be fairly easy. Do as much as you can. Some of these, the math relationship, using y equals mx plus b with velocity and so forth. And then you get down here. This is where it's going to get a little bit harder now. So on your graph here, we're going to graph average velocity here, velocity instantaneous on this one here. And tells you in the directions there which one's which. So for the first one, your average velocity, once you get it from up here from 0 to 6 seconds, your time is going to be the same on both of these. Your velocities are not. So whatever your average velocity you get from above from 0 to 6, put that as your maximum. So if you draw a line from 0 to 6 and it's 30, like on our previous worksheet at the beginning, put your maximum average velocity at 30, and that'll help you out with that. And then over here, for your instantaneous velocity, if I remember correctly, let me look back here, I think it asks you to draw or figure out your instantaneous velocity at 4 seconds. And I think what I did was at 4 seconds is I scaled this out to 4 seconds, and I went up and put a dot where that time was and then drew a line through that. Your maximum velocity on this one, this is going to be 3 meters a second. So you're going to have 6 seconds here, 3 meters a second here. And then go ahead and graph that. If you don't get this part, that's fine. It's going to take some thought working through, like, how are you going to, if you look at your slope, if your slope is 30 meters for every second, that means it's traveling 30 meters at every second. 2 meters is going to be 60 and so forth. So you could do it that way. There's multiple different ways you could do this. Okay, so try to do this. Now the problem down here, I'm going to give you an example similar to this. Now you can solve these without any formulas, and that's the greatest thing about doing the modeling physics, is you don't have to memorize all these acceleration formulas. So I don't think I gave you guys this before we left. We might have had the XT and VT, but we didn't do the AT. I don't remember. So anyways, here it is, and there is more to this, but this is just to keep this simple. This is all we need to know to do these. So up here you have your graphs, your XT, VT, AT graph. Your slope meaning of these. Well, if you take your units, position is in meters, time is in seconds. Meter over second equals velocity. So the slope of your XT graph is the velocity of the object. On your VT graph, well, velocity is in meters over a second, time is a second. That means the slope of this graph is acceleration. And then for the slope of an AT graph, we don't know what the meaning of that yet. If you're in calculus, there's a specific term they use for this. And you guys probably already seen this, but most of you probably haven't. There's only a couple of you that were in calculus. The area meaning. So of an XT graph, the area of that underneath that line, we don't know what that meaning is, if there is one. We're not someday possibly. Of a VT graph, well, if you take your y-axis, which is a meter over a second, times your time, because you're finding the area underneath that, if it is a rectangle, so length times width times a second. So meter over a second for velocity times time. The seconds cancel out. That means we're left with a meter. That means a change in position. Now the area for acceleration time graph, we have meter over a second on our y-axis. Our x-axis, we have time, which is a second. So it means the 2 seconds cancel out. We're left with a meter over a second, which means we have a change in velocity. So an example of this, here we have a graph, velocity, time. Okay, here we have the slope. We know the slope of this, slope of a VT graph means acceleration. The area, this is a right triangle. So area equals half the base times the height. Area underneath this is our change in position. So we can move backwards to this graph. So let's say we have a hypothetical situation here. I have an object that is traveling very fast, and he slams on the brakes, and it takes him 6 seconds to stop. In that 6 seconds, he traveled 30 meters. Now, knowing our formula for this area, we only have one variable unknown right here. So I take area equals our half the base times the height. My area is 60 meters. Half my base is 6 seconds times my height, which is my unknown. So you solve for h now, and you end up with 30 meters a second. So the object was traveling at 30 meters a second when he slammed on the brakes, and it took him 6 seconds to stop, and he covered 60 meters. So this is similar to this problem right here. All right. So go ahead and do as much of this as you can. Take a picture. You can either email it to me or send it to Google Classroom. If you have any questions, feel free to shoot me some emails. Like I said, I'm very confident you guys can get everything. These two graphs here might cause you a little bit of headache, but I think I gave you enough information to help you out there. All right. And if you have any questions, like I said, don't feel like you can't shoot me an email. I usually answer them throughout the day. Have a good weekend.